Okay, guys, Professor Bryant back. Another installment of Workout Wednesday. We're still on nuclear chemistry. I wanted to do an example that utilizes application of half-life for a radioactive nuclide or isotope. The problem that we're going to be looking at is 21.37 from the text. It tells us that cobalt-60 is a strong gamma emitter, right? It emits gamma radiation. And it has a half-life of 5.26 years. Obviously, that's going to be important value for us. They tell us that the cobalt-60 in radiotherapy unit, which is in healthcare, must be replaced when its radioactivity falls to 75% of the original sample. So that's another value that we're going to be interested in. If an original sample was purchased on June 2016, when will it be necessary to replace the cobalt? So we got a couple very important pieces of information here. First thing they've given us is half-life. So it's always good to write down what we have. Half-life is equal to 5.26 years. All right. They've also told us that we are interested in 75%. And if we remember from our equation that ln of the amount of moles, or the amount at time t, is equal to negative kt, this ratio here is what this 75 is. So we're actually looking for when the ratio of NT to NO is equal to 0.75. Again, remember, this is a function of the ratio. Again, this is first order kinetics, and they haven't given us an amount to start with because they don't have to. They've given us this fraction. This fraction is very important. So whenever you see a percentage, remember, percentage has to do with this ratio. So NT over NO is equal to 0.75. The only thing that we do not have is K, but we can calculate K using the half-life. So K is equal to 0.693 all over the half-life, which is equal to 0.693 divided by 5.26 year, and that value K is equal to 1.3175 times 10 to the negative 1 year to the negative 1. Remember, keep track of your units. I'm going to always suggest keeping plenty of significant figures when we're dealing in nuclear chemistry because a lot of these numbers are going to have a large amount of sig figs. Okay, so now that we have K, we know the ratio and the time that we're interested in of 75%. We can solve this equation for T, which is what we're looking for. T is equal to when CO needs to be replaced. And to solve for T, we end up with T equal to E raised to the negative KT times excuse me, I did the math wrong. T is equal to negative ln of 0.75 all over K, which is 1.3175 times 10 to the negative 1. Okay, again, this is plugging in 0.75 and plugging in K. All I did was the mathematical manipulation of this here. Okay, and we see that this is equal to 2.18 years. Again, this is year to negative 1. Keep your units. And if we think about 2.2 years effectively, then we're dealing with something. If they said July 2016, then after 2 years, we know we're in 2018, and about 0.2 of 12, right, is about 2 months or a month and some change. So we're talking about August-ish 2018. But the important value here is going to be 2.18, right? 2.18, so that we know we can solve for T given the information. So this is a question of application of half-life calculation using values and ratios. Again, if you have any more questions on half-life in the nuclear, be sure to send me an email or a comment on the video.